we are back with solutions. So solution typically has two things mixed together. We have a homogeneous mixture between two different things, which means, of course, a single phase, no clear phase separation. Solutions can be a solid in a solid, like alloys, like brass. It can be solid in a liquid, like salt dissolved in water. It can be a mixture of two gases with each other. Um, when you have a solution, must have at least two parts. We call the part that's present in lesser amount the solute, and the amount that's present in greater amount the solvent. And the solubility, of course, is the amount of solute that will dissolve in a given amount of solvent. Usually when we talk about solutions, we're talking about solids dissolved in liquids, or maybe another liquid dissolved in a liquid. And solvents is a term we typically use when we're talking about liquids. Solutions, we have a number of different units that we often use for solutions. A few that you're familiar with and you've seen before. The first one, molarity, which is the one we almost always use, which is moles of solute dissolved by liters, total liters of solution. We also have mole fraction, which is basically the moles of solute over the total moles of solution. We can have mass percent. You see sometimes this is maybe a little less frequently encountered in chemistry, but you do see it quite a bit. For example, if you go by a case of beer, the mass percent of alcohol is typically what's listed on the side. Or maybe that's volume percent by volume. Anyway, one new one that we're going to be discussing in this unit is molality. And molality is used in very specific examples because it has some advantages over molarity. Molarity and molality actually converge to being the same number when you're at very dilute solutions. The difference with molality and molarity, actually that's only true if the solvent is water, between molarity and molality, that they are the same at very dilute concentration. But molality is moles of solute divided by kilograms of solvent. And so volume actually doesn't even come into play with molality at all. So these are just a couple of hints if you need to convert between, and I unintentionally drew over some of these, but these are some hints if you want to interconvert between these different units, and we're going to do a few problems where we do exactly that. So why would we ever want to use molality versus molarity? Well, one thing is that if you are looking at a solution defined by molarity, because it's defined by moles of solute divided by total volume or liters of solution, the volume of a solution is not constant when temperature changes. So in other words, if you warm up a solution, it tends to expand. When you cool down a solution, it tends to contract. And this can actually change your molarity because it's changing the volume without changing the number of moles of solute. Molality, on the other hand, a kilogram of solvent will weigh the same regardless of what the temperature is, so it's temperature independent. So it has that going for it. So we're going to jump right into this problem. It says, what's the molality of a 5.86 molar ethanol solution whose density is 0.927 grams per mil? So let's take a look at this one. Well, what we can do is if we assume right at the beginning that we have 1 liter of solution, this means we have 5.86 moles of ethanol. And I'm going to abbreviate ethanol as ETOH. And the total mass of solution is going to be our 1.00 liters, just assuming 3 sig figs here, multiplied by the density, And what we can actually do is change that if we want well, the units here don't match, so we need to make this 1,000 mils, 0.927 grams per mil. Now we can cancel these, and we have 927 grams of solution. So that solution, remember, is made up of solvent and solute. We know how much of that is solute. So we could say the mass total so we can get the mass of the solute from the moles of the solute, which is up here. And I'm going to just change this to mass of ethanol, because that's our solute. And that's going to be equal to moles times molar mass, which is 5.86 moles, multiplied by the molar mass of ethanol. Molar mass of ethanol is what? Quick search gives me 46.07 grams per mole. And that gives us a total of 270 grams for ethanol. So what does that mean for our moles or mass of solvent or solute? No, solvent. That's going to be equal to our total mass, which is 927 grams, minus our mass of solute, which was 270 grams. And that equals 657 grams, which is 0.657 kilograms. So now what we can do is calculate the molality. Molality is often written as a small m, usually in italics, which is a bit confusing because it kind of looks like a lowercase molarity or an italicized mass, but I'm going to do my best here. That is equal to moles of solute over kilograms of solvent. Our moles here is 5.86, which you can see at the very, very top. Kilogram of solvent is 0.657 kilograms, and that equals 8.92 molal. Now, that's our answer that we're looking for. One interesting thing here is we never actually talked about what our solvent is. You might have assumed it was water, and maybe it was. Turns out, though, it doesn't matter. The molality of the solvent doesn't matter what the solvent actually is. We just need to know what the mass of that solvent is. Okay, so when we have molality, this has nothing to do with molality. We're talking about when one solution will dissolve in another. And we kind of touched on this before back when we looked at intermolecular forces. Usually we can kind of go by this rule of thumb, which is that like dissolves like, which means if you have two substances that have similar types of intermolecular forces available to them, they tend to be soluble in each other and form a single homogeneous phase as opposed to separate phases. That means nonpolar molecules will tend to be quite soluble in nonpolar solvents. And an example here is carbon tetrachloride and benzene. Both of these have no dipole moments, and they can be mixed together in any proportion. The word for that is miscible. Polar molecules will be much more soluble in polar solvents. So an example we have is ethanol from our previous example dissolved in water. Ionic compounds, for the most part, are usually also soluble in polar solvents and insoluble in nonpolar solvents. Of course, not all ionic compounds will be soluble. We have a whole solubility table which explains which ionic compounds will be and which ones won't be, but they're generally all insoluble in nonpolar solvents. All right. How do we actually think about this? Well, if you think about a solvent, one solvent molecule, like you see here, will be, I guess I can use my little pointer here too. Maybe I can't. Will be attracted to another solvent molecule by intermolecular forces. Solute molecules will be attracted to other solute molecules by intermolecular forces. So in order to dissolve one in the other, what you have to do is sort of break solute-solute interactions and break solvent-solvent interactions, and you trade those for new solvent-solute interactions, like you see here, right? Because this, if you look at this one, it's sort of wedged in between two solvent molecules. Those two solvent molecules are no longer attracted to each other because the solute butted its way in between. So generally speaking then, if you have solvent-solvent and solvent-solute interactions that are stronger than the solvent-solute interactions, then typically solutions don't form. If they're roughly equivalent, solute-solvent, if you're breaking solvent-solvent, solute-solute, and trading them for solvent-solute interactions, typically a solution will form if it's otherwise equal. This solution formation is usually driven by entropy, because entropy would be increasing by forming the solution, and that is thermodynamically favorable. Also, if you have solvent-solute interactions that are much stronger than solvent-solvent interactions, then a solution is definitely going to form. That's driven typically by both enthalpy and entropy, which makes this go quite well. Next slide. Stop it, stop it, stop it. Oh crap. Why is it doing this? There we go. Okay, good. Get rid of that. Whew. Common laboratory solvents. So this is just a list of solvents that we typically use in chemistry labs. Certainly not an exhaustive list. There's a much longer list of liquids that we normally use. For polar solvents, things that are hydrogen bonding, like water and alcohols, like methanol, ethanol, isopropanol, things like that. Acetone is also a fairly polar solvent. Acetone has this chemical structure. There's other polar solvents that are not on this list that we would use. Dimethyl sulfoxide, several others as well. For non-polar solvents, we have things like carbon tetrachloride, which used to be very common. It's not anymore because it was banned by the Montreal Protocol in 1998, I want to say, which has made it extremely expensive. It's a bad ozone depleting substance, so we're not supposed to use that anymore. Hexane is used quite a bit. Other alkanes as well. Toluene, benzene is less frequently used, but again. Then we have diethyl ether. And diethyl ether has an oxygen, you can see right there. I would say it's more intermediate. It's not very polar, but it's not very non-polar as well. We have lots of solvents that fit into that sort of in-between category, like diethyl ether. Tetrahydrofuran, ethyl acetate. There's lots of sort of in-between substances in there as well. So this is just a quick exercise on predicting solubility. Predict the relative solubility of the following mixtures. So if you have bromine, Br2 in benzene and in water, we're going to predict which one it's going to be more soluble in. So the way you would look at that is look at each of these substances and identify them as being polar or nonpolar. Br2 is nonpolar. Benzene is also nonpolar. Benzene has a structure that looks like this. Typically, hydrocarbons, if all you have is carbon and hydrogen, especially very symmetrical ones like benzene, they're going to be nonpolar as well. And water is quite polar. It's the poster child for polar liquids. So we would expect bromine to be very soluble in benzene and not very soluble in water. It's a little bit soluble in water, but not very soluble. KCl, which is an ionic salt. In carbon tetrachloride, which is nonpolar. Remember, carbon tetrachloride will have a tetrahedral structure. And what happens is we have a number of polar bonds. All the CCl bonds are polar, with the chlorine being the more electronegative atom. But because of the direction and the symmetrical shape of this molecule, all of these bond dipoles cancel out. So there's no net dipole, so it's nonpolar. Ammonia is polar. In fact, it's hydrogen bonding. So we would expect KCl to be much more soluble in ammonia than it would be in a nonpolar liquid like carbon tetrachloride. Part C, we have formaldehyde, and formaldehyde has this structure. And we're looking at carbon disulfide, which has a linear structure like this. This is nonpolar. And in water, which we know is polar. So formaldehyde itself is quite polar. That carbon-oxygen bond will have a good, strong dipole because of the electronegativity difference between carbon and oxygen. So we would expect formaldehyde to be more soluble in water than it would be in carbon disulfide. All right, I think we're going to take another break here and just leave you with this page, which is another set of very similar sorts of questions to the one we just looked at. You guys can take a look at that and then pause the video if you want, take a look, and then we'll get in with the rest of the chapter before too long.